Hello everyone, I'm Ravish and today we are going to discuss what is the bias variance trade-off. This is one of the most asked interview question in machine learning interviews, and the reason behind that is like this is directly related with the concept of improving the performance of machine learning models. So professionals love to ask this question to any newcomer because they want their teammates to be sure about why exactly their model is underperforming, why exactly they are not able to like their model is not able to perfectly fit the data set that they are having. So this is the day-to-day challenge of any machine learning engineer, and I have also 6 years of experience in working in this area. So based on that experience, I have sat on multiple interviews on both sides of the interview table, and I have never found any such interview who is not asking this particular question: what is the trade-off between bias and variance? So today we are going to discuss that topic in a greater detail, and after understanding this topic, you will feel much confident in clearing machine learning interviews. Okay. So before going any further, let's first understand these two terms. What does that mean? Like the two terms are like bias. One is bias and one is variance. And before understanding these two terminologies, we have additional two terminologies. One is underfitting, and then second is overfitting. Now, underfitting has a direct relation with bias, and overfitting has a direct relation with variance. So that's why we will first understand these topics in greater detail. These two topics, these are not two topics, these are two different problems with which any general machine learning model is actually suffering. And we invest a lot of time as a machine learning engineer, we invest a lot of time improving these problems and then like applying techniques to resolve these problems and then reach at a position of low bias and low variance. We will talk about all these in a short while. Okay. So let's first understand the problem of underfitting. Okay. So let's take quickly one data. So suppose we have one data x equal to 1, 2, 3 until this 10. Okay. Now suppose we have another, the labels corresponding to, because in a supervised learning problem, we have input data and corresponding labels as well. The labels corresponding to this input data is 1, 4, 9 and till 100. Okay. So you can easily observe that the relationship between output variable and the input variable is nothing but y equal to x square. Okay. So this is something like a parabolic function. If you know about the degree concept, this is a 2-degree polynomial. Now, if a 2-degree polynomial, our expectation from our machine learning model is that it should predict a 2-degree polynomial itself. Now, suppose we provided some kind of this data to our machine learning model, but it actually suggested, or it actually by default, it actually thought like I will predict only 1-degree polynomial, or maybe not even 1 degree. It will predict only one particular value corresponding to this particular data. Like suppose if we try to like plot it, something like around a parabolic function will be something around like this. Okay, this is the kind of data and we want our machine learning model to fit this something like this. Please remember, in machine learning we do not want anything rather than reducing the error between predicted value and actual value. Actual values are nothing but the corresponding labels that we have already present in our data set, and then predicted values is something like when a machine will try to identify this relationship, it will try to identify one relationship between x and y, and then based on that it will like design a function and then give the predicted value corresponding to each and every x. Like suppose somehow our machine found that it only predict one particular constant value, like suppose something like this. This is a constant value. Okay, this is nothing but a constant value. Let's say this is y and this is x. This is a constant value. The error between predicted and the actual values will be very high here. You can easily sense, like for this sample, like suppose for this sample, the actual values are here and then predicted values will be here. The difference between the gap between these two values are very wider. So we can say that error will be very higher in that case. So what exactly we want? We definitely do not want our model to only predict one constant value. Like suppose one constant value was something like y equal to theta naught. This is the prediction, and machine learning model will try to learn this value theta naught based on the data that we have. Okay. Now we will say that no, this is definitely underfitting. This is not fitting the data that we had. So that's why we are saying that this is underfitting problem. Now suppose we will try to improve the complexity, or maybe like add few of the terminologies. Now suppose we don't want and like this kind of prediction. We want to add additional term y equal to theta naught plus theta 1 x. In that case, what will be the predictions according to you? So in that case, like suppose we will have the prediction something like this. And suppose we will have the prediction something like this. Still, do you think that this error will be in like the actual values and the predicted values will be lesser? No, definitely not. Because still, if you will find for this particular value, the predicted values are around here, but the actual values are here. So still the gap is very wider, right? Actual versus error is still higher. Now, what we will do, we will again add additional term to increase the complexity of our machine learning model so that it will become able to find a 2-degree polynomial in that case, theta naught plus theta 1 x plus theta 2 x square. So in that case, it has become a 2-degree polynomial. Now, in that case, if we have the input data is something around this, our model will be also able to try to find, or like will be able to find some kind of data around this. So in that case, if you will observe, the error become very lesser. And this is what exactly we wanted from our machine learning model. Okay. And this is the appropriate fit, what exactly we were like expecting our machine learning model to learn. So, but if you observed earlier, the complexity was very less. We were learning only one constant value. Okay. After that, we increased the complexity slightly by introducing one additional term of theta 1x, but still that was not sufficient according to our data. But when we increase the complexity more, like by introducing another term of x squared, which is a kind of 2-degree polynomial. This is 0-degree polynomial, this is 1-degree polynomial, and this is 2-degree polynomial. So in this case, our error become very much lesser, and this is what exactly we wanted from our data set. Okay. So now, if you quickly observe this particular scenario, like suppose we are plotting the size of the house, and based on that price of whatever will be the price of the house. So now, if our model is like predicting something like this, like suppose it is not doing anything, it is predicting a constant price in that case. So this will be a kind of underfitting scenario. Okay. So what exactly we need to do here? We need to increase the complexity. Now, let's see one additional example as well. Here also, in the this is a classification problem where we need to classify the two different data samples, cross samples and dot samples. Like suppose this is class 0 and this is class 1. And model somehow tried to predict only 1-degree polynomial based on this 1-degree polynomial. 1-degree polynomial means linear line. Based on this linear line, it tries to separate these two classes so that whenever a new sample will be above this line, it will classify it as a kind of class 1, and whenever a sample will be below this line, it will try to classify it as a kind of class 0. But in this prediction, you can easily observe that many of the samples are misclassified. Like these samples, this one, this one, this one, this one, this one, this one. And these two classes are also misclassified. They should be present in the class 1, but they are present in class 0. But all these cross classes are should be present in the cross class, which is class 0, but they are present in class 1. So this is a huge error. Okay. We want higher degree polynomial to be fitted on this particular data set so that our error become lesser. Okay. So now we have understood what is the underfitting problem, but let's first understand what exactly is the reason behind this underfitting. So we know the underfitting is a problem in machine learning, but what is the reason because of which our model is suffering from the underfitting problem? Okay. So what happens? Let me give you one example of underfitting scenario, which is very relevant and you will quickly identify what is underfitting in that case. Like suppose we are providing 1000 images. Our expectation from our machine learning model is take the image of any animal and then predict whether it is a bird and not a bird. Okay, only two classes are present, bird, not a bird. In that case, like suppose if an animal is there, we are providing image of that animal and then based on that it is categorizing bird and not a bird. But in this 1000 images, we provided 900 images of bird class. So after passing this much image of the bird class and only 100 images of not a bird class, so model started assuming things. Okay, our machine learning model, our ML model was not that smart, and it started assuming that all the classes are bird class. Okay, so in that case, it started assuming some kind of those things which we were not intended our machine learning model to do. But somehow it found out that by like predicting always the bird class, my like task of predicting the classes between bird class and not a bird class will be very much easier. So that's how what exactly it did. It always predicted the bird class. So this is something like our prediction is biased towards bird class. We can say that our model is highly biased here because it is always predicting the bird class, and whenever a new image is come, it will always say this is bird. So we can definitely say that in this case, our machine learning model is highly biased. Now we learned why exactly the underfitting problem is arising because model is assuming too many things from our data set. Okay, so but there can be another possible reason of underfitting can be like like suppose we have given what exactly we want from a machine learning model, but we want machine learning model to find the relationship between input and output. We want to find this relationship which is fx, this function. But in some scenarios what can happen is like there is no any existing relationship between input and output. What does that mean? There we cannot even after so many research cannot find this relationship because there is no such relationship between input and output variables. So in that case ml will not be able to find the relationship between input and output variables. If there is no any existing relationship between input and output variable, how will machine find? So in that case, what exactly are the two problems because of which underfitting issues happens? There exists no relationship. No relationship between input and output variables. And the second is we have that model, our model complexity is very much lesser. These are the two possible reasons because of which underfitting happens, or maybe we can say that bias increases in our machine learning model. Okay, any problem till this position? So no, so bias increases. Okay, now what are the possible solutions in this case? The possible solution, we understood the reason behind these problems, so now our responsibility is to find the solutions. What are the possible solutions that we can apply here to resolve these issues, this underfitting issue? The first solution that we can think of is like introduce features. This introduction of features will try to give some kind of relationship between input and output features. This introduction of features means like we will have to engineer features or maybe try to find more number of features from the original data set, or maybe try to engineer features from the existing data set so that machine will be able to find the relationship between input and output. Okay, the second solution is like increase the model complexity, and this is the more primer concern for this particular lecture. Increase model complexity. Okay. Once we increase the model complexity, our model will start forming some kind of bigger polynomial or maybe fitting a bigger polynomial data, and it will be able to classify it. Okay. So this will be our perfect fitting data set. This is currently underfitting because many samples are misclassified. So let's understand. We have understood the underfitting problem, the reasons because of which the underfitting occurs, and then possible solutions for that. Okay. So let's understand the overfitting problem as well. So overfitting, during overfitting, what exactly happens? We try to fit a function which is too complex for that data set. Okay. So let me quickly give you one example here as well. Like suppose in a data set which was y equal to x square, we were trying to fit y equal to theta naught plus theta 1 x plus theta 2 x square plus theta 3 x cube, or maybe theta 4 x 4. So for a 2-degree polynomial, we were fitting 4-degree polynomial. Okay. And because of this fitment, what exactly was happening? Definitely, the error was becoming lesser on the data set. Error means like the difference between the predicted and actual values. So the difference between predicted and actual values were reducing. So that's why we were saying that the error is decreasing, and like our model was doing very perfect in that case. But this was not the case. If we observe, we have generally 3 data sets: training data, validation data, and testing data. Let's forget the validation data for now. Okay. On training data, we use this data for learning the relationship between input and output variables. Machine uses this training data to train on, finding the values of different parameters. Now, once that parameter is being learned, we need to test the performance on the testing data also. Definitely, in overfitting scenarios, the error on the training data will be very smaller because we have fitted a very huge model on a very simple data set, and because of which the error between predicted and actual values are very lesser. The training data fitment is not an issue for us. But what will happen when we will test that particular learned parameters, when we will test that model on the testing data, the error will be very higher. So let's quickly understand what exactly happened here. So we tried to fit a very complex model on a simple data set. So what happened? Like suppose this is the data that we had. Okay. And if you know the signal thing, whenever we record some kind of data set, like suppose we are recording some uh, data features. Okay. So what we will observe, there will be no any fixed data samples. There will be some kind of scattered values. Okay. This kind of thing. So what will happen if we try to fit a very complex model? It will start. So any sensor will have some kind of noise values. Okay. These noises will be present in our data set. So very complex model, what very complex model will do? It will start learning the noise values as well. To fit the data very perfectly, it will start learning the noises as well. So in that case, if you will observe here, the curve of like suppose this green curve. So if we trace it, it has like recorded or learned the noise values as well, rather than it would have only recorded this particular functions, which was the original function that we intended our machine learning model to find. But as our machine learning model was too complex, it can learn any relationship between the existing data, the relationship between input and output variables. So it started learning everything, whatever is present in the training data. But when we applied the same learning on the testing data, it failed to perform that better. So we definitely don't want this scenario, because our overall objective is to that model performance should be always better on the testing data, not training data. Training data is our uh, like uh, data which is we are currently using for training the model. But when we will deploy it on the real life scenarios, the testing data is what exactly matters. Okay. So this is something like we definitely do not want our model to like learn everything, every noises that are present. So in this particular scenario, what will happen? So if you will observe, So how exactly this is related with the high variance we are talking about that. So currently, what exactly is happening? Model is too complex to learn everything in the training data. Okay. And the second probable reason because of which this high variance can come is like the train set and test set are different. Like whatever is present in the training set, there is no such correlation with the test set. The test set is a different set and train set is not lying, or there are no common scenarios between train and test set. So in that scenario, whatever machine will learn from the train data, it will never be able to apply the same learning on the test data. So these are the two problems because of which overfitting issues actually happens. Okay. So now, how exactly this is related with the variance? So in this particular scenario, what will happen? Like suppose whenever we will try to like there are two kinds of equilibrium, if you know, like this is one stable equilibrium and one is the unstable equilibrium. Unstable equilibrium is something like this. Like whenever our model is here, like suppose this is the stable equilibrium, when we will push it into this direction, it will never come into this position again because it will fall and it will reach to some other position which is stable equilibrium in that case. But here, if we will try to push it into this direction, it will again fall in this direction because this is stable equilibrium, and that's what exactly we want our machine learning model to be. Okay, I will quickly explain what exactly does that mean. So suppose our model is predicting something. Okay, suppose our model is predicting one value. We are providing one input to our ML model, and it is giving me some kind of predicted value. Now, whenever we will slightly change the input values, slight change means just addition of one noise, suppose, just addition of few of the variations in the input features. And in that case, if we will try to pass the same data with just slight change with the same ML model, it will predict a value which is drastically different from the earlier predicted value. The same input with slight variations, the predicted values are changing by a lot. So we can say that definitely that uh, our machine learning model is not that stable. It is suffering from high variance case. Like if we vary the input data slightly, the predictions are very much fluctuating, which we definitely do not want. We want our predictions to be stable. And that's why we do not want our model to learn the noise values, because of which it is suffering from the overfitting problem. So that's why we want our machine learning model a very stable model so that whenever a slight change will happen in the input signals, the predictions should not change that much. So that's why we want to lie in a condition of low variance. Okay. So we learned about two different problems. The problem of underfitting was like overfitting was because of high complexity model, and the train and test data sets were different. Now we will learn about the possible, like let's quickly take one additional example as well. Like this is the complete price and house price and size data set. On this data set, if we try to fit this degree polynomial, 2-degree polynomial, suppose, which is here, this will still be perfect. But if we will try to fit the same data set with a 4-degree polynomial, it is something like this. The training data error will become very lesser, but testing error will become very higher. So in that case, the model is suffering from the overfitting problem. Now, what are the possible solutions using which we can reduce this overfitting scenarios? One is increasing the data. because we did not have those scenarios. Like one possible reason was testing and training data were different. These two sets were different. So that's whatever machine learning model is learning from the training data, it was not able to apply that learning on the test data. So if we try to increase the training data or suppose increase the overall data, it might be a possibility that those scenarios which were present in the training set should also come into the testing set, and then machine will start performing better. So in that case, definitely increasing the data will be helpful here. The second approach is like reducing model complexity. You can easily observe the same scenario here. Earlier, we were fitting 4-degree polynomial. If we try to reduce the complexity by removing these two terms, suppose we will try to remove these two terms altogether, and then it will simplify our model, and that's how our model fitment will be very much easier, and the overfitting issues will be solved. Reducing model complexity will be helpful. Let's quickly discuss what will happen if we try to increase the data, that whether it will solve the underfitting problem or not. Please understand, this is underfitting. I'm asking underfitting. So definitely not, because in the underfitting scenarios, if you have observed, what exactly we were trying to do, introducing features, not the data samples. If we try to increase, so whatever data we had, there were no such relationship between input and output variables, and that's why machine learning model were not able to find the relationship between these two. If we again try to increase the samples, data samples, then also there will be no such relationship. Our model should find the relationship between existing data, then also if we try to increase the data, then it will try to find the relationship between these two as well, the increased samples. But as we did not have that kind of uh, like capable model of which was able to find this relationship, even if we try to increase the data, the underfitting issues will never be resolved. But definitely the overfitting issues will be resolved in that case. So this is something like very important question for machine learning interviews. They ask, if suppose we try to increase the data, whether it will solve the underfitting problem or not. Definitely it will never solve the underfitting problem, but it will solve the overfitting problems. So if you observe, so there are two scenarios. In the overfitting scenario, we want our model to be very complex so that it will start finding the relationship between input and output features. But in the overfitting scenarios, we want our model to be less complex so that it should not start learning too much things from the training data and fail to generalize it on the testing data itself. So that's why let's quickly understand one very like what exactly we want in that case. So we want just right fitting, like in the same data set that we have discussed earlier. So in the same data set, like suppose this is the right fitting that we want, even though there are some misclassifications, but that will not affect the testing data performance. So that's why we want the just right fitment for our data set. Okay, just right fitment for our data set. Now quickly learn, this is the scenario that we want. We definitely do not want overfitting, and overfitting was introducing the high variance case. Our model has become very much unstable. Whenever a slight change in input is happening, then the predictions were varying by a lot. So we definitely do not want this kind of scenario. We want our predictions to be stable. Okay, and we definitely do not want underfitting, because with the case of underfitting, our model was high bias, highly biased towards one of the classes, whatever is present. We saw in the bird example as well. So let's quickly understand this particular very famous diagram that is being used in this bias variance trade-off concept, which is bullseye diagram. This is known as bullseye diagram. So let's quickly understand how exactly this is the scenario of low bias, low variance, and high bias, high variance. What exactly we want? We definitely want low bias and low variance. That will be the perfect fitting data set. Okay. So that's the objective which we want to achieve by reducing the problems of underfitting and overfitting. So let's quickly understand what exactly is the problem. So, but before that, let's understand low bias and low bias, high bias, and low variance, high variance concept using the bullseye diagram, which is something like, if I will tell you, let's quickly understand. Like if we change the input slightly, the variations are, or the predictions are varying too much. It is scattered, not confined in a very highly defined range. Okay. So if suppose we have defined range of the predictions would be like around this particular circle, if we can easily observe that predictions are very much confined in this boundary, so that's why it is a low variance case, because predictions are not varying too much. not scattered here and there. It is very much confined in a like very much defined in a confined boundary. So that's why we are saying that this scenario is a low variance scenario, and this scenario is a high variance scenario. Similar to that, our predictions here are not scattered too much. It is confined in this boundary. If we try to like put a boundary around this, our predictions are not too scattered, but here our predictions are very much scattered. So that's why we can definitely say that this model is suffering from high variance. This model is suffering from high variance. Okay, and this is low variance and this is low variance. So this is the scenario that we actually want. Now quickly understand the low bias and high bias as well. This is very interesting because not many you will not find this on many places, why exactly these two are corresponding to low bias and high bias. Now when you will see, when you will try to plot a central diagram or central dot in this position, you will quickly find that your predictions are lying all around this dot. Like suppose this direction, this direction, this direction, this direction, or in all directions we have certain kind of predictions. But here, if you will try to plot the like central dot here, you will quickly find that your predictions are always above, not lying in this direction, in this direction, in this direction, but highly biased towards this direction. It is always lying above this central point. So we can definitely say that this prediction is highly biased towards the above direction. But this is definitely not, because our predictions are lying all around our central point. And the same scenario is here. Like if you will plot the central plot, in all the directions predictions are there. We are not saying that predictions are not there in the like below direction, right direction, left direction, above direction. No, predictions are lying all around this particular dot, central dot. But when we will talk about this scenario, our predictions are highly biased towards this direction. All the predictions are lying in this direction, and there is no such prediction in this direction, this direction, this direction. So we can definitely say this model is definitely suffering from high bias, and this model is these model are not suffering. These model are becoming in the condition of low bias. These models are falling in the condition of low bias. So definitely, what exactly we wanted: low bias and low variance, which is this scenario. Okay, here our model is not suffering from high variance because our predictions are confined in a defined range, and our predictions are lying all around the central dot. So because there is no such bias, so we wanted a low bias and low variance concept, and that's the perfect model that we wanted. Okay, so let's quickly understand one mathematical terminology, because of which everything we are discussing is quite relevant. This MSE, what is MSE? MSE is the mean squared error. Okay, what is mean square error? Error we have defined like the difference between y predicted minus y actual. Okay, so this is the difference. This is error, definitely. When we will square it, it will become something like this. Now suppose we have 100 such samples, like 100 samples in the data set, so that this error will be like calculated for all the 100 samples, definitely. So in that case, we will have to find the overall error. Overall error will be summation of all these errors. Summation of all these errors for 100 samples. And this is the complete summation. We wanted mean out of it. So we will have to divide it by 100 to find the average error for every sample. And our objective in machine learning is try to reduce this overall average error. Not single error, not single sample error, but the average error. Please understand. We always wanted our machine learning model to focus on average error to be reduced. This is the cost function. And when we will try to write this cost function, this error in terms of bias and variance, we will identify that this will come something like this: bias square plus variance plus irreducible error. Irreducible error is nothing but, like suppose the data annotation part. Okay, data annotation is nothing but for every input variable, like suppose we saw 1, 2, 3, 4, 100. For every input sample, there should be some kind of output variable as well, like 1, 4, 9, something like till 10 until this 100. Okay, so for every input sample, there is a perfect labeling of samples as well, the corresponding labels of y output. Okay, so in some scenarios, like suppose in one scenarios, sometimes people get confused between cat and dog. There is a very high probable chance some human is assigning label that this image corresponds to cat and this image corresponds to dog. But sometimes that human can be confused by looking onto the images, and it might be a possibility that dog image will be classified as cat and cat image will be classified as dog. But as we are learning from that data set itself, so our model will never be able to find, because that is the truth value, that is the true labels. and we are learning from the true label. So that's why our model will not be able to completely resolve this kind of error. So that's why we are saying that this is irreducible error. It will always be present, whatever in whatever manner. If we try out many complex models as well, this error will still be remaining the same because this is present in the data itself. Now, coming to the two parts, bias and variance, we want MSE to be smaller. So that's why we want bias to be lower and variance to be lower. Both the things should be lower so that MSE will become always lower, because we cannot touch irreducible error. So that's why we wanted some kind of mechanism to reduce the bias and reduce the variance. But there is the catch. So if we have learned very carefully to reduce the bias, we want to increase the complexity of the model, but to reduce the variance, we want to reduce the model complexity. So there is a trade-off. If we try to increase the complexity, bias term will increase. Sorry, bias will decrease, but variance will increase. If we reduce the complexity of the model, variance will decrease, but bias will increase. So this is the trade-off. If we try to plot everything, like if we try to increase the model complexity, like by introducing more and more degrees, like theta 1 x plus theta 2 x square plus theta 3 x cube. So if we try to increase the model complexity, definitely the bias will decrease over when we will try to increase the complexity. But at the same time, variance will increase. But when we will talk about the opposite scenario, when we will try to decrease the model complexity, bias will increase, but variance will decrease. But definitely we want both the things to be lower so that our MSE will be smaller, because our objective is to reduce the error between predicted and actual values. So in that case, there is a trade-off between model bias and variance. So this is the trade-off that we were discussing throughout this session. So that's why we want optimal model complexity. This is another problem, which is why we are discussing this topic. We want to identify what should be the optimal model complexity to completely or perfectly fit our data set. And as if we try to increase the complexity, bias variance trade-off starts working. So that's why finding this optimal model complexity becomes a challenging task, and that's why people in the professional industry try to find the optimum model. Finding the optimum model can be increasing the complexity of the same model by introducing more and more parameters, or changing the models altogether. So these are the two possible scenarios. Okay, so I hope you have understood this particular trade-off existing between bias and variance very cleanly. So let's quickly understand how you will decide whether your model is suffering from the underfitting or overfitting problems, or your model is suffering from high bias scenario, high variance scenario. Okay, like suppose there are two sets: training set and testing set. Now, this training set and testing set are two different sets that we have. Okay, so our model can be like, suppose for a let's define a baseline error as well, like the irreducible. With that irreducible error, there will be some kind of human error, because of which we were discussing that few of the errors will be irreducible throughout the machine learning process. We will not be able to resolve these, okay, because of the annotation issues. But let's define that particular line as a kind of our baseline, which is human error. But definitely these errors will be very much lesser. So let's say that it is 99% accurate model. Humans are 99% accurate. And our model will be most effective when it will reach at a position of 99% accuracy. Okay, so we will try to find a model in which the training error and testing error both are 99. Or maybe we can say that training accuracy and testing accuracy both are at the 99%. Okay, so, but when we will try to develop these kind of models, we will quickly observe that if the gap between human error and training error is the error on the training data set. If this error is very large, and when compared to the human error, this gap will be very huge. If this gap is very huge, means our model is not learning the data set, not learning the patterns present in our data set. So that's why we can definitely say that our model is underfitting. Okay, when the gap between human error and the training error is very high, then the scenario will be falling under the condition of underfitting. The same thing is like, again, the overfitting scenario. It might be a possibility that we applied a very high complexity model and achieved suppose that we became able to like reduce this gap. The gap between human error and training error becomes lesser. Training error become lesser. Like suppose training error become 95%. So definitely this is very much very closer. 4% of gap is there. Earlier, like suppose this is at 50% accuracy and this was at the 99% accuracy. So definitely when we will talk about the gap between these two and these two, this gap is very much lesser when compared to this two. But at the time of, like suppose we applied more complex model and tried to reduce this gap and achieve this thing 99 to 95%. But when we will when we tested our learned model, trained model, the gap between training error and testing error was very huge. Testing error, we observed that it is still at 50%. So the gap between training error and testing error is still very huge. In that case, our model is suffering from overfitting problem. Okay. So this overfitting problem is something like when the gap between training error, our model was able to find the relationship between by using the training data, but failed to generalize that learning on the testing data. So that's why the gap between training error and testing error is very huge. So that's why our model is suffering from the high variance scenario, which is overfitting problem. And the possible solutions you definitely know. So let's quickly discuss possible interview questions on this topic. So one possible interview question: what is the bias variance trade-off? This is the most important question because many interviewers will ask this question, and we now know, like if we try to improve the variance, bias gets increased. If we try to reduce the bias, but variance gets increased. So there is a kind of trade-off between these two, because of which when we try to improve the complexity of the model, variance gets increased, bias gets reduced. When we try to improve the reduce the complexity of the model, bias gets decreased, variance gets bias gets increased and variance gets decreased. So we want both the things to be lower, and that's why we want to find an optimal model complexity, and that's the bias variance trade-off. Okay, how do we solve the underfitting issues? Definitely, increasing data will not help here. So that's why we want to engineer features and then increase the model complexity. These are the two possible solutions there. How do we solve the overfitting issues? Reducing the model complexity and increasing the data will also help here. The two solutions that we discussed. How do we find that the model is suffering from an overfitting and underfitting problem? So the same thing, by using the gap between zero error, training error, and testing error. We can easily define these errors, and whenever the gap between zero error and the training error is very huge, we will say that model is suffering from underfitting. When the gap between training error and testing error is very huge, we will be saying that our model is suffering from the overfitting issues. Okay. If we increase the data samples, will it solve the high bias problem? Definitely not. We have always discussed increasing the data will never solve the bias scenarios. It will always solve the variance scenarios. So please remember this. I hope I am able to solve your queries and make you understand this beautiful topic of bias variance trade-off, and you have understood it very clearly. Thanks.